Hello everyone, welcome to my channel. I'm Dr. Q. In this video, we will review the marginal analysis to make optimal decisions. We will also review the method to figure out marginal, taking derivatives. Like you have learned in the principles of microeconomics, we use marginal analysis to decide how much effort to devote, how much resources to use, or how many units of products or services to produce. We denote this variable of interest as Q, quantity. Then, the manager's goal is to maximize the difference between the benefits of doing so and the cost of doing so. How to achieve that? We must make sure the extra benefits associated with doing so equal the extra costs arising from a change in a managerial control variable Q. Alternatively, it is marginal benefit equals marginal costs. So this is the marginal principle. To maximize net benefits, the manager should increase the managerial control variable Q, quantity, up to the point where marginal benefits equals marginal costs. This level of the managerial control variable Q, quantity, corresponds to the level at which marginal net benefits are zero. Nothing more can be gained by further changes in that variable. How do we figure out the marginal effect? For a continuous function, graphically, we have a smooth curve. Then the marginal value of the function at a certain point is the slope of the curve at that point. Mathematically, we can take the derivative of the function at that point. For example, to figure out the marginal effect of quantity on benefit, we take the derivative of total benefit, denoting derivative, taking derivative. B is total benefit with respect to Q, quantity. Marginal cost of quantity is the derivative of total cost with respect to quantity. And the marginal net benefit, which is the extra difference between total benefit and total cost associated with one more unit of quantity, it is the derivative of the total net benefit with respect to the quantity Q. Here's a graphical illustration of the relationship between the slope of the total and the corresponding marginal value. The orange curve is the total product with respect to the number of workers hired. So the horizontal axis represents the quantity of labor. The blue curve is the corresponding marginal value. For example, if we want to figure out the marginal product of hiring the fourth worker, like how many extra units of output the fourth worker can bring us. On this total product curve, we can see this is a curve as opposed to a straight line. So it's not very easy to figure out the slope. For a straight line, we can easily figure out by the change on vertical value over the change on horizontal value, or rise over ramp. But this is a curve as opposed to a straight line, so what we do? We can imagine that there is a very short straight green line that happens to be tangent to the orange line at the 4th unit of labor, which means the green line and orange line share the same slope just at this point. Then we can calculate the slope of the straight line, which is the rise over run, or vertical change over horizontal change, to approximate the slope of the orange line at labor of 4. I can go ahead and tell you that the slope at this point equals the corresponding marginal product at labor of 4. The slope of this green line is the slope of the orange line at this point, and the value of the slope, it is the value of the corresponding marginal product. Then we can see that as orange line, total product becomes steeper, which means that slope is larger. The corresponding marginal product is larger. Then the total product becomes flatter. The marginal value declines. And when the slope is negative, the product is negative. We can say that the total product plateaued, means achieve its maximum value whenever corresponding marginal product equal to 0. So the total achieve its extreme value here is maximized. In some cases, like it is minimized. Extreme value whenever corresponding marginal value is equal to 0. Mathematically, we take derivative to figure out the marginal effect. I'm here to introduce a useful rule, which is the power rule. The basics is that if the dependent variable y is a function of a variable of interest x to the power of c is any number, then if taking derivative of y with respect to x, we simply move the power c in front of x as a coefficient, then the original power minus 1. That's the power rule. Here are some examples. The first one, the dependent variable y equals the summation of a constant number beta 0 and beta 1 multiply the variable of interest x, beta 2 multiply x squared. If we want to figure out the marginal effect of x on y, we need to take derivative of y with respect to x. The first component, beta 0, we can ignore it because it doesn't have any x in it. If you really want to figure out, alternatively, you can rewrite the beta 0 as beta 0 multiply x to the power of 0, because any number to the power of 0 is 1. So x to the power of 0 is 1. 1 multiplied beta 0 is beta 0. Here just illustrate how you can see x is not in here, so beta 0 does not influence the result. Then beta 1 multiply x to the power of 1. So anything power of to the power of 1 is itself. The third one is obviously that to the power of 2 square. Now, we take a derivative according to the power rule. The first component, we move the power 0 up front as the coefficient, then the whole term is 0. The second component, move the power 1 up front. It's still power 1. It's still beta 1. And then x to the power of 1 minus 1, which is 0. X to the power of 0 is 1, so beta 1 itself. And the third one, we move the power up front. And original power minus 1. So this is what we got. 0 multiply anything is 0. And 1 multiply beta 1, x to the power of 0 is 1, so beta 1 itself. Then 2 beta 2x. This is the answer to this question, taking derivative of y with respect to x. Here's another example. Y equals beta 0. Apparent beta 0, just ignore it. Plus beta 1 multiply the inverse of x. We can ignore the beta 0 as it does not involve x. The second part, we can rewrite it as beta 1 multiply x to the power of a negative 1. So the negative 1 is the inverse. Then move the negative 1 power up front. And original power, negative 1 minus 1, we got negative 2. So this is the answer for taking derivative of y with respect to x on this functional form. Now, back to economics. Here's the total benefit function and the total cost function with respect to quantity, like output. We want to figure out how many units of output we should produce. What is the value of Q that will maximize the net benefit, which is the difference between benefit and cost. Normally, that's our profit. We want to use the marginal analysis that marginal benefit equals marginal cost. The first step is to figure out the marginal benefit by taking the derivative of total benefit with respect to Q. And according to our power rule, we can figure out. The marginal benefit has two parts. The first one is 250 multiply Q to the power of 1. The derivative of this part is 250. The second part is negative 4 multiply Q to the power of 2, Q squared. Move the power 2 up front as coefficient. Negative 4 multiply 2 is negative 8. And original power minus 1. So Q by itself. The second part is negative 8Q. The marginal cost is Q squared. Total cost is Q squared. So marginal cost is moving 2 up from 2. Original 2 minus 1, so 2Q. Then make the two of them equal to each other, solve the equation. We figure out the optimal output level that maximizes the net benefit is 25. Here's a graphical expression of the functions. This is a total benefit curve, eventually declines, and total cost curve increase, but total benefit doesn't decline with a constant number, and the total cost does not increase with a constant number. When the two of them cross each other, which means total benefit equals total cost, we're at the break-even point. And as we learned that the total benefits are maximized when it plateaued. But the point we care about is whenever the difference between the two of them is maximized. We can see that when the slope of a marginal benefit equals the slope of the marginal cost, the net difference is maximized. If you can imagine the difference between the total benefits and total cost is a balloon, and if we tilt it clockwise by 45 degrees, then squeeze the bottom part up flat, we'll get this net benefits curve. Net benefits are maximized whenever marginal net benefits are zero, or the slope of the net benefits is zero. That is whenever marginal benefits equals marginal costs. Here are the graphical expression for the marginal curves. We can see that whenever the marginal benefits equal marginal costs, the marginal net benefits are zero. Here's a practice. It asks you to write out the equation for marginal benefit with respect to Q output based upon the total benefits function here, which is 100 plus 36Q minus 4Q squared. Please pause and try, and then come back for the answer. All right, this is the answer. Take derivative of total benefits with respect to Q. Ignore the part without any Q. And 36 minus 8Q is the marginal benefit. Now, the total cost curve function is 80 plus 12Q. Please write down the equation for the marginal costs. Pause and try. All right. This is the marginal cost function. Pretty straightforward. Lastly, please figure out the output Q that maximizes the net benefits. Pause and try. All right, we use the marginal analysis that marginal benefits equal marginal costs and figure out output. Optimal output is 3. Further, it asks you at the output where net benefits are maximized, what is the value of the marginal net benefits? Please see if you can figure out yourself. All right. Now, according to what we learned before, when the marginal benefits equal marginal costs and net benefits is maximized, the marginal net benefits is equal to 0. All right, thank you for watching this video. please subscribe to the channel. I will see you in the next one.